Hello, everyone, and welcome to this lecture in the Hands on Large Language Models series. Today, we are going to look at the second type of semantic search, and that is called as re ranking. So, let me quickly recap the three types of semantic search which we have been looking at in this lecture series. The three types of semantic search, or rather, the three broad categories of how we can use language model for search, are as follows. The first is dense retrieval, where we just look at the query. So, here is how dense retrieval works. We have the query, that query is converted into a vector, and we have our document base, and each of those documents are then converted into vectors, and then from among these vectors we look at that particular vector which is closest in distance to the query. Now, what is that distance? It can be a Euclidean distance, or it can just be the cosine similarity. This is how dense retrieval actually works, and we have seen two videos on dense retrieval before. We saw how dense retrieval works, and we saw chunking itself and the importance of chunking with respect to dense retrievers. Today we are going to see re-ranking. So not many people actually understand how important and just how useful re-ranking is. But first let me explain what exactly is re-ranking. Well, re-ranking is just one of the multiple steps in a search system, where let's say that someone has already built a search system, right? Let's say um, someone has built a search system which operates as follows. So a query is given, then you have the dense retrieval which we have seen before, and that retrieves a certain set of, let's say, top 50 documents. One, two, three, and that retrieves top 50 documents. Let's say this has already been implemented, but that particular person or that particular company or startup who has implemented this, they are not very happy with the results which they are getting. They look at the results and then they look at the query and they think that, well, the results don't really make too much sense. Can I use some other thing after this which looks at these results and which looks at the query and then which re-ranks them? So can I find another method here which essentially looks at the documents, looks at the queries, and assigns a relevance score? So let's say the relevance score to the first document is, let's say, 50. The relevance score to the second document is 60. The relevance score to the third document is 45. Then 2 and 1 will essentially be interchanged. So then document 2 will come at the top, 1 will come below, 3 will go at the bottom, etc. So let's say we assign some sort of a relevance score to all of these documents, and then the re-ranking is performed based on that. This second step of the procedure, which comes after some sort of search has already been done, that is called as re-ranking. That is why the re comes into the picture, which means we are assuming that some sort of ranking has already been done before, or we have certain small set of documents which already exist, and now we just need to re-rank them. This is the procedure of re-ranking, and that is shown here in the format of a schematic. So we have a query, and we already have a small number of relevant texts. This adjective small is very important here, because earlier when we are querying, we are looking at all of the huge number of documents. Then we have certain search system where small amount of those are already present with us, but we are not happy with the order. That's where the re-ranking algorithm or the re-ranking approach is implemented, and then the document order is changed based on the relevance score. So re-rankers, the second key type of semantic search, takes a search query and a collection of results and reorders them by relevance, often resulting in vastly improved results. So let me scroll down below now and let's come to the section on re-ranking which we had planned for today. Yes, now what we saw was that re-ranking is used by organizations and startups which have already built some sort of search systems, and they want to add another method on top of it which makes their search system efficient or which makes their search system better, right? So, for such companies or organizations, an easier way to incorporate language models is as a final step inside their search pipeline, just what we saw in the re ranking schematic above. So, the re ranking step is tasked with changing the order of the search results based on the relevance to the search query. So essentially, what is done is that, let's say if we have a certain set of documents, yeah, let's look at this. Let's say if we have a certain set of documents, right? All of these are the initial results which we've obtained from the first stage of search. Then let we take the first document, and we, along with the query, a certain relevance score is assigned to it. That's called R1. Then we take the second document. Again, it is compared with the query, and a score is assigned to it, R2. Similarly, a relevance score is assigned to all the documents, and then based on this relevance score, the re-ranking is performed. Where now the top document has the highest relevance and the bottom document has the lowest relevance. So, if you are watching this lecture closely, remember I told at the start that re ranking vastly improves search results. Now, when I studied re ranking for the first time, I did not honestly fully understand the importance of it. What are we really changing here? We are just re ranking, right? We are reordering. How is it so different than this first search which we have done? It might be a dense retrieval or a keyword retrieval or just a hybrid search of dense plus keyword. How is it so different? Why does a small step like this make so much of a difference? So, just as another point before answering this question, Microsoft Bing has added re ranking to their search results. So, if you go to this page, I'll share the link. Semantic re ranking, semantic ranking in Azure AI search. So, here you can see that in Azure AI search, semantic ranking is a feature that measurably improves search by using Microsoft's language understanding models to re rank the search results. See, again, this word is coming here, re rank. So, why does re ranking vastly improve the search results, and why is re ranking so important? Well, I had to dig a bit deeper to really understand the meaning of why is re-ranking so different than dense retrieval, right? So if you look at dense retrieval, what is happening is that, let's say we have a document A that is converted into a vector embedding, correct? We have a document B that is converted into another vector embedding. Then this document is then after it is converted into a vector embedding, then it is compared with the query, and we see how close or how far it is from the query. Now, if you have a document B, we perform a vector embedding, and then it is compared with the query. So let me actually write a schematic of this. What happens in dense retrieval is this. So you have document 1, you have document 2, and let's say you have 50 documents. All of them are converted into vectors, vector embedding spaces, correct? Now, the key thing here is that when these documents are converted into vectors, they have not at all seen the query. A large language model is used to convert these documents into vectors, but they have not yet seen the query. That's the most important point here. What happens after this is that, so once they are converted into vectors, the query is also converted into a vector. And after both of these are converted into vectors, then we look at the query and the document, and then we see which document the query is the most closest to. Now, this is the main part where re ranking actually differs. In re ranking, what we do is that, let's say we already have these 50 documents. So we have document 1. So then we look at document 1 and plus the query together. And then we find a similarity score. We assign a relevance score, let's say R1. Then we look at document 2. Then we look at document 2 along with the query. Then we look at document 3 along with the query. Similarly, then we look at document number 50 along with the query, and then we assign a relevance score. Do you see the difference here? If we just perform dense retrieval, whenever we get a vector embedding for the document 1, it has not yet seen the query at all. We just get this vector embedding and then find the distance. But here what happens is that the document, each document and the query together go to the transformer, or together go to the embedding model, or together go to some sort of a large language model. They together go to a large language model which assigns a relevance score. See, so when the large language model operates, it looks at the document and the query together. But here, when the large language model operates in getting these embedding vectors, it only looks at the document. It has not seen the query at all. That's why using dense retrieval, sometimes we may get results which do not make too much sense. But re-ranking solves this problem because we look at the document and the query together before they are fed to the large language model. This blog here mentions this very nicely, right? So this is what happens in dense retrieval, where document is fed to an embedding model which is also called as a transformer here, and vectors are generated. Let's say for document A the vector is generated, for document B the vector is generated, and then we find the similarity score. But in the case of re-ranking, this is what happens: the document along with the query is fed together to the transformer or the large language model, and then we get the similarity score. That's the biggest difference between re-ranking and dense retrieval. So let's read what is written here. In dense retrieval, we have no context on the query because we don't know the query until we receive it. We create the embeddings before the query time. This is very important. These All these embeddings in dense retrieval, these are created before the query is even received. Whereas a re-ranker can receive the raw information directly into the transformer or the large language model computation, so that leads to less information loss. Because we are running the re-ranker at the user query time, we have the added benefit of analyzing one's document meaning specific to the user query rather than trying to produce a generic averaged meaning. What this means is that when we use re-ranker, the large language model which we are using, it has the document and the query together. So that's why it can look at both and assign a relevance score. And that's why the relevance score will definitely be an appropriate relevant score related to how is the document actually relevant to the query. So that's why dense retrieval sometimes gives us meaningless results. And when we add this small step of re-ranking, it drastically improves the result by a huge order of magnitude. This is the thing which you definitely need to understand, the difference between dense retrieval and re-ranking. Now, this type of dense retrieval is also called as a bi-encoder. This is called as a bi-encoder because we are doing encoding of the query and we are doing encoding of the document separately. They are not fed in together. That's why this type of dense retrieval is also called as bi-encoder, whereas re-ranking is also sometimes called as cross-encoder. And the reason this is called as cross-encoder is that because we are encoding the document and the query together at the same time. So it's called as document is being encoded at the user query time, which means document and queries are encoded together. That's why this re-ranking is called as cross-encoder. So essentially, when re-ranking is integrated into a search pipeline, we may be doing bi-encoding first, and then on top of that, we are doing cross-encoding step. It's very important for all of you to understand this distinction before we move to the coding part. All right. I hope all of you have understood up till this part, where we have understood how re-ranking differs from dense retrieval, how re-ranking can be a second step in someone's search pipeline, a startup or a company. Thirdly, we saw that re-ranking is already used to improve AI search for Microsoft Bing, and I am quite sure it might be used in Google search also. Now, what we are going to do is that we are going to code in Python, and for coding, as always, we are looking at this interstellar Wikipedia example as text. So, what we are doing is that we are looking at this entire text and we are using different methods to ask queries to this text. So remember I told about documents before, document 1, document 2, etc. Each sentence in this text will serve as one document for me. So this first sentence is the first document, second sentence is the second document, third sentence is the third document. So we are using sentence level chunking, and then after a query is asked, we are returning the most suitable document. We have done this using dense retrieval, and today we are going to do it using re-ranking. And then, so we are going to do two things in code today. First, we are going to take that interstellar Wikipedia. We are going to break it into sentences, and we are going to apply two things to it. First, we are going to take this entire documents and apply re-ranking without any other step initially. Although I told you that re-ranking comes after dense retrieval or some other search step, I just want to show you how re-ranking works. If you directly operate it on text level documents, it also works very well. And then we are going to do keyword search, and then we are going to add re-ranking on top of it. So in this second example, I'll show you how adding this re-ranking step drastically improves the results of the keyword search. So we'll jump into code, and we are going to use this cohere API key for the re-ranking as well. So let's jump into Google Colab code right now. All right, so this is the Google Colab interface, and we have been following this hands-on large language model book by Jay Alamar. As always, we have to load this initial set of packages such as LangChain, FAISS, which is Facebook AI semantic search. Then we have to load BM25, which is an algorithm for keyword matching, sentence transformers, and Llama CPP. This we won't need right now, but it's just better for you to go ahead and install all of these libraries so that you can run all the codes. The next thing is that we are going to do re-ranking today, and for that we are going to use Cohere. There are different platforms which give you re-ranking related tools. Cohere is one such platform. It's called Re-Rank API, and you need the Cohere API key for this. So you can sign in here, and once you sign in, you will be taken to this section where your API keys will be shown. You can just copy this key and paste it over here. I am not currently showing this API key here for privacy or for security purposes. There are other platforms also through which you can retrieve your API key. So, for example, there is a platform called Pinecone, and you can even use Pinecone for re-ranking. And you can get the API key from Pinecone as well. And so see, you can get Pinecone API key as well. You can feel free to try this after watching this lecture. But for the purposes of today's lecture, I am going to use Cohere just for the reason that the people who have written this book, the authors who have written this book, have used Cohere. So that's why I am also using it. All right. So the first thing is you have to import Cohere, paste your API key here, and create the Cohere client. Right. The second thing which all of us need to do is that you go to Wikipedia, copy this text of the three paragraphs, and paste it right over here. Okay. Or you can just run what I have mentioned in this Google Colab notebook. Then what we have to do, as I said, we are doing sentence level chunking here. So every sentence is going to be one document. So we have to split this text into a series of sentences and add it to a list. So we are creating a list called texts, and each element of this list is now one sentence in this entire text. All right. Then what we have to do is that let me now go to the re-ranking. Okay. So now the text is the list which has the different sentences. Now I want to do re-ranking, which is I want to do the first step here where I have broken down my text into different sentences or chunks, and now I want to use the re-ranking algorithm. So what is done here is that as I told you, when you put a query, the query along with the query and the document one together will be seen by the LLM, and then we have a relevance score. Then the query along with document 2 is seen by the LLM, and then we have another relevance score. So now you might be thinking that why is dense retrieval even used in the first place? Why don't we get rid of this entirely and just have re-ranking as we are doing in code right now? The reason why re-ranking is not done at the first step is that re-ranking is very slow. Re-ranking is very slow. So re-ranking is only done after you have retrieved a small set of documents after the first stage. So in the first stage, you have millions of documents here from your text archive, and let's say you retrieve a small number of documents. So re-ranking is only used on those small number of documents because it takes a huge amount of computational time. So let's see the order of magnitude here. It's actually mentioned over here. If we have 40 million records and if we use a re-ranking model, we'll be waiting for more than 50 hours, right? But if we just use encoder models, like if we do dense retrieval and do a vector search, this same operation can be done in less than 100 milliseconds. So that's one trade-off which comes with re-ranking. It's a slow algorithm, and that's why it's always performed on a small set of documents. For the code which I'm demonstrating right now, here we only have 20 sentences. So let's see. Yeah, we only have 15 sentences actually. So even if you directly implement re-ranking, it's totally fine. But this will not work in real life examples. You should not directly re-rank. You should first implement a dense retrieval, maybe select the top 1000 or top 500 documents, and then implement the re-ranking algorithm. So here what we are doing is that let's implement re-ranking directly on the text archive, because we only have 15 sentences which our documents or main document is broken into. So then this query plus document relevance score only needs to be done for 15 times, because we have 15 sentences or we have 15 documents, right? So we have the query now, which is how precise was the science. And if you look at this text which I have, the only place where this is kind of mentioned is that it has received praise from many astronomers for its scientific accuracy. So actually this is the only place which talks about science precision. So the query is how precise is the science, and ideally this should be retained, because nothing in this text actually talks about how precise the science is apart from this one sentence. All right, so now let's see. So we are using query how precise was the science, and then we have to use this cohere.rerank. So this client, cohere client, is called CO, which we have defined over here. See, right over here, CO is equal to cohere.client, and we have given the API key, right? So here I'm saying co.rerank. So which means that we have to pass in the query, we have to pass in the documents, which is the texts, and we have to say that how many documents need to be returned. So I'm saying that we have to return the top three documents over here after the re-ranking has been performed. So let's say you can see the results over here. If you want to print out the results in a good format, you can do enumerate results.results, and you can print out result.relevance.score and results.relevant result.document.text. So remember I told you about this relevance score. Currently the way we have written the code is that we want the top three most relevant documents, and we also want to print out their scores. So this is exactly what has been done here. So the first most relevant document it is that it also has received praise from many astronomers for its scientific accuracy. This is exactly that sentence which we looked at is correct. So if you remember, we looked at the text and we saw that there is only this one sentence which is related to scientific accuracy, and our re-ranking algorithm has correctly recovered that sentence. See, it has also received praise from many astronomers, and the score is 0.17. Whereas if you see the second sentence and if you see the third sentence, the re-ranking score is very low, which means that the re-ranking algorithm which we have used has, or the LLM which we have used, is saying that I'm quite confident that the only sentence or the only document out of your list of document which matches the query quite well or is most relevant to the query is this sentence. The other two sentences are slightly relevant, but the relevance score, so the relevance score of the second is almost more than 50% lower than the first, and the relevance score of the third is extremely low. It is 100 times lower than the first, so we should not even consider this third document. If you have done the dense retrieval example, you must have seen that we also obtained relevance score here, or rather we obtained the distances, but see the distances which were obtained here were very close to each other, right? So although the answer given by dense retrieval is correct, the distance for the other two was also close to the distance for the dense retrieval. So it's very difficult to look at the other two and say how bad they really were. But now, using the re-ranking, we can see that the score which has been obtained for the remaining two documents is very low, which means that we are quite confident that the first document is the correct one. So re-ranking is actually gives results which are much better in meaning compared to keyword search, but the only downside of re-ranking is that it takes a lot of computational time. Now the second thing which I'm going to do here is that I'm going to now do keyword search first and then do re-ranking. To recap your understanding, keyword search is essentially just looking at different keywords and not dealing with meaning. So before semantic search was introduced, people did keyword search. So if I search shows such as Stranger Things, so if I go to Google and search shows like Stranger Things, in semantic search which is done right now, Google or the search engine understands the meaning behind what I have asked. So it understands that when I say shows like Stranger Things, I am looking for shows maybe which are set in a small town which have a mystery element. But in keyword search, what we do is that we just look at documents which have the word stranger, which have the words things in it, and those are returned. That's not very good, right? But let's say we want to do keyword search and then improve the results by doing re-ranking. That's how actually it is done in practice instead of directly using re-ranking. So for keyword search, the most popular algorithm is this BM25 algorithm, which is used for keyword search. And instead of looking at the meaning, it just looks at term frequency, average document length, etc. So what we are going to first do is that we are going to use this BM25 algorithm, and we are going to give the top three results from BM25. I don't want to go into the details of how BM25 works, but essentially what we have done in this code is that created uh, take the passage and tokenized it using the BM25. So we have created a function called BM25 tokenizer, which takes this passage, breaks it down into individual words or tokens, and then we apply the BM25.get scores. So it does kind of like a lexical search. It's also another term for keyword search. So what we are going to do here is that we are going to apply BM25 algorithm and we are going to get the top three documents for the same query. The query is how precise was the science. And then what we are going to do is that uh, the top three documents which we get, we are going to call them docs. And then we are going to apply the cohere.re-rank to these docs which have been returned from BM25. And then we are going to print out the results. That's all. Okay, so I hope you understood the procedure. What we are going to do is that we are going to take this all these 15 sentences. We are going to first apply BM25 algorithm, which is also called as lexical search. It is called as lexical search or keyword search. And after this, we are going to get the top three entries. And then on these top three entries, we are going to do the re-ranking, and we are going to assign relevance scores to each of these, and let's see the order which, if re-ranking improves the results. So the results are here. So this function is called keyword and re-ranking search. So if you apply this function to the query, you will see that just with the keyword search, here are the answers which are obtained. How precise was the science? The answer which is given the most priority is Interstellar is a 2014 science epic science fiction film, right? It is not at all related to the question which we have asked, which is expected because we are doing keyword search. The second is Caltech theoretical physicist and Nobel laureate, and the third is Interstellar uses extensive practical. So these are all answers which are actually not related to the question. But now let's use the re-ranking API. So now we use the re-ranking API, and re-ranking tries to change the order. So according to re-ranking API, the first is Caltech theoretical physicist and Kip Thorne was executive producer, acted as scientific consultant, right? So although this also does not match the question quite well, it is still closer to the question than the first answer. So now the re-ranking just has these three sentences to work with, right? So it does the best which it can do. And this is the re-ranking score: 0.004, 0.004, and 0.003. Here you can see this score is not at all closer to the highest score which we have obtained. But that's the drawback of using the keyword search at the start. You only got these three documents. So now you only have the re-ranking algorithm only has these three documents to work with. And it tries its best to reorder these so that we have sentences which make sense at the top. So re-ranking makes it a bit better because Nobel, if a Nobel laureate is there, it means the science might have been precise, right? So the meaning is captured. So this sentence is a much better answer to the question than this sentence. So what we prove from this exercise is that re-ranking improves The quality of keyword search. Re-ranking improves the quality of keyword, or it is also called as lexical search. This is very important to realize and understand. So I'll share this code file with all of you where we have run two codes. The first is we directly ran the re-ranking without combining it with any other search method. And there we saw that the answers were amazing. The top answer was given a much higher similarity score than the bottom, indicating the confidence with which we have retrieved this answer. But if we chain re-ranking with keyword, it definitely improves the quality just compared with keyword search. But it's not the best because re-ranking only has these three answers to work with. So I hope this lecture gave you an understanding of re-ranking. First of all, the takeaway should be that re-ranking is very different than dense retrieval. So just remember this in mind. In dense retrieval, it's a by encoder model. So we take documents, convert them into vectors. Maybe let me show it over here. Yeah, we take documents, we convert it into vectors. We don't see the query until this time. Query is only seen later, right? So that's why the results which are produced are sometimes not very meaningful to the query. But in re-ranking, the document and the query are seen by the large language model or the transformer at the same time. So that's why the results are much, much better. Or rather, I should say the relevant scores make so much more sense. So just this small step of re-ranking can completely improve your search results. So if you are a startup or if you are any company who's introducing large language models for doing search or retrieval, you are not getting good results. Just integrate the re-ranking pipeline on top of it, like how Azure AI did for Microsoft Bing, and you will see a huge improvement in results. And I hope I've convinced you why you see these improvements in results. That's because both the document and the query are fed together to the transformer at the same time. Another thing to remember is that re-ranking, although it encodes the meaning very well, the only drawback is that it takes a huge amount of computational time. So if you want to do 40 million records, if you just use re-ranking directly, it will take more than 50 hours. But if you are using by-encoding models such as the dense retrieval, for example, then it will take less than 100 milliseconds. So it's like 100,000, even 1,000, 10,000 times faster. Just keep this drawback in mind. That's why if you always see the schematic of re-ranking, right? Let's see, if you always see the schematic of re-ranking, see it's mentioned small number of relevant texts. So re-rankers always operate on small data because their computational uh, time is very high. Then at the end of the lecture, we looked at hands-on coding examples where we saw two codes, two approaches. First, we just used re-ranking on the entire interstellar dataset, and then we did keyword search plus re-ranking. And in both, so re-ranking just use alone gave us great results because the number of documents or sentences was very less. When merged with keyword search, re-ranking definitely improves the quality of keyword or lexical search. So just towards the end, I want to mention that re-ranking can be very powerful in improving the search quality. And not only that, as has been mentioned in the book Hands on Large Language Model, on a multilingual benchmark like Miracle, re-rankle can boost performance from 36.5 to 62.8. So it can improve the performance of search algorithms by two times. We'll understand what this NDCG and all means in the next lecture, which will be about evaluating re-rankers. So until now, we just saw how re-ranker performs, right? But what are better ways to evaluate this re-ranking results, whether the results are good, whether they are not, etc. So we'll be looking at re-ranking evaluation. So how re-rankers work and how so it's also called re-ranking evaluation matrix or retrieval evaluation matrix. So for both dense retrieval and for re-rankers, how to know whether the results which you have got are good or not. So there we use some metrics which are called as retrieval metrics. We'll have a separate lecture on that. But for now, I want to end this lecture with saying that in today's class, we have already understood how re-ranking models work, right? We present the query plus each result to a large language model. The large language model assigns the relevance score, and then the re-ranking is done. So it works something like this. The query and the document is fed to the re-ranker. And when we say re-ranker, we have a large language model here. And then the large language model assigns the relevant scores, and based on that, the ordering of the documents is done. The first paper which introduced re-ranking is this paper called multi-stage document multi-stage document ranking with BERT. And let's see. So this paper was published, I think, in 2019. Facebook AI research in collaboration with New York University and University of Waterloo. I highly recommend you to read this paper. It's also sometimes called as monobert. So this architecture is sometimes referred to as monobert, which essentially introduced re-ranking. Another good paper which I will recommend you is pre-trained transformers and text retrain transformers for text ranking. Yeah, BERT and beyond. This another great paper to read. So one of the major objectives of my teaching classes is that you should learn the concepts, you should learn how to code, but at the same time you should be involved in reading recent research papers. So re-ranking is also sometimes referred to as monobert. You should definitely read this monobert paper, and you should definitely read this paper, pre-trained transformers for text ranking, BERT and beyond. Both of these are highly impactful papers, and after this lecture you'll find that reading these documents is easy, uh, since you have the understanding and if you have also run this code from today's lecture. Thanks a lot, everyone. In the next lecture, we'll look at retrieval evaluation metrics, and after that, we'll start covering retrieval augmented generation. In many lectures and in many videos, they directly start with RAG, which is retrieval augmented generation. But that's not the best way to teach RAG. First, you have to teach dense retrieval, then you have to teach re-ranking, and only then you have to teach RAG. So I'm following the same framework of teaching here. I'm teaching dense retrieval first, then re-ranking, and then RAG. So thank you so much, everyone, and I look forward to seeing you in the next lecture.